dynamic will be equal to 1 plus Gm of, let's call that transistor Q2. Gm of the 2 multiplied by Re multiplied by the Ro of the Q2. So what we used to have in here, which was just the Ro of one single transistor, in this format, the dynamic resistance between the collector and the reference ground will be way, way higher because it will multiply by the influence of that resistance and the Gm of that circuit. That's the bottom line with current sources. Improved or increased dynamic resistance with the help of a resistor at the set bias point. How is this thing is biased? There are many ways of doing it. One can take voltage divider, the same good old fashion that you calculated DC current in the common emitter amplifier, R1, R2, set it up. It could be resistor with a Zener diode in here, biasing the Zener. Zener biases this, which is the ref, or a few diodes put together. You can create a voltage difference between the 2 points, and therefore on the Re, therefore a current in the Re, which is the current in the IC. But because of this Re, we will get gigantic improvement on the dynamic resistance. And today what I'm doing in here is going to show you influence of that dynamic resistance. How does that influence the common mode voltage gain? How does that reduce the common mode voltage gain? So this problem is analyzed already with every detail. I think in your problem number 6, and homework 6, problem number 7 over there. So what we have is a transistor stage. We've got about 1.1 milliamp current going down, and we are calculating the differential gain of this amplifier. In other words, differential gain means if you put two separate voltages at the positive, one at the negative, V1 and the V2, and you apply, what will be the output voltage divided by the difference of the two? That's called the differential voltage gain. We can do that, but now here, putting emphasis on how do we calculate the common mode voltage gain with existence of that constant current source, its dynamic resistance as Re, and we are putting a common voltage simultaneously to both, to this model here. Notice B2 is connected to B1, a common voltage. Let's see what will come out of the deal. Okay, so common goes to both simultaneously. Let's see what comes out of the deal. That output divided by input is defined as A, the common mode voltage gain. And we want that guy to be as small as possible, so that it will basically, when we're amplifying the differential, we will have significant gain at the output. So how do we go about it? It's very simple. First of all, DC analysis. We don't need much for that one. It's given as 1 milliamp. Resistance is about, I think 100 and, where it shows you, 130 something kilo ohm, anyway. So how do we analyze to get to the formula? This is the model for both transistor, draw them. Put all constant values to 0. Remember the signals. You put DC values to 0. Please, this is a DC value, constant value. So you 0. When you 0, it means disappears from the screen, okay? So when currents are zeroed, they're out of the circuit. They're non-existent. So there is nothing in here, no constant current there. because this is an AC motor. Resistors are not. RE sits over there. Transistor, R pi, RC, R pi, and RC, because that current splits half and half between the two. They have identical R pi's, identical GMs. So we get all parameters that we need. Now, how do we analyze it? Take a KVL, VCOM, so it's this voltage, negative to positive, that's the VCOM. IB, R pi times IB is the current in here, in the transistor Q1. There is also another IB in here for the second transistor. The two are equal IBs. Why they are equal? Symmetry. This circuit is completely symmetrical. Right? So you get two identical IBs over there. So KVL around this loop. VCOM minus R pi IB, you're here. You come over here. You have 1 plus beta IB from that branch, 1 plus beta IB from the second transistor. They come in, they combine into 2 times 1 plus beta IB multiplied by RE. You have 2 times of all of that. And this makes the, you can calculate IB from here. So once you figure out the IB in terms of the VCOM, that's this current also. You multiply it by beta, beta times of that here, and then you multiply by RC, this RC. That will be your final output voltage. VO, substitute from here to here. Here you are. VO over VCOM is minus beta RC, R pi plus 2 times 1 plus beta RE. This is our ACOM, the common mode voltage gain. It's a finite value. What is the finite value there? A good simplified value. Please note, like before, 1 plus beta is multiplying RE, right? RE is already a gigantic resistance. So it doubles, so it becomes even more larger. Dominates R pi, because R pi's are about a K or 2K. So this disappears. If that disappears, look what you have. You have beta over 1 plus beta at the bottom. That ratio is 1 if beta is high enough. Isn't that right? Beta over 1 plus beta is nearly 1. So bottom line is ACOM, to a great approximation, is RC divided by twice of RE. End of the business. So common mode voltage gain of a differential amplifier. Here's how you would decide. If you had it like this, here, 2 transistor, V2, V1, supply, output, VO. If you had it biased with a simple resistor RE minus VCC plus VCC, if I asked you what is the ACOM, ACOM, this would be the answer. You need to bring a formula sheet. This is not the big formula. Finished. That's your common mode voltage gain. So it means if you join the two together, if you connect this to one point and you name that a common input, VCOM, still you will get a voltage at the output over what you're putting in. The ratio of output over input, like voltage gain, would be whatever you have RC divided by the twice of the RE. Finished. That's it. If you had it a current source, you know, one of those mirror image current source with its DC current and everything, after you're done with the biasing and all that, you want to know what is the CMRR, you will go check out RO of that transistor. So if this transistor was a regular one and the VA was given, and you know what is the VCE, and it doesn't influence that much either, and you know what is the I that it is sourcing, you could easily calculate the RO. That RO would replace the RE. Okay? Here. Same formula. Right there. If you had it, this arrangement here, better one, this guy, with that transistor replacing the current source, because now collector is sourced with this arrangement. Then the dynamic resistance here would be 1 plus GM of that transistor times the RE that you're placing in the emitter path, multiplied by the dynamic resistance between collector and the emitter, just like before, collector and emitter. Except here, collector emitter resistance shows as the dynamic resistance. Here, collector emitter resistance is enhanced by this quantity, shows as the dynamic resistance of that current source, which is significantly high. Okay, so those are the variations. If you understand, you can work with it. See, that's how to use it, that's what the formula is. So for this problem, we even have a common mode input resistance, RICM. So what is that? Whenever you're putting a voltage at a point and you see current flowing in, ratio of the voltage to current defines input impedance. So we do have an input impedance known as the common mode input impedance. And that common mode input impedance is VI here, VCOM, which is this voltage, VCOM, divided by ICOM. ICOM is 2IB, because there are two base currents, signal base currents moving from that load. One for transistor 1, the second for transistor 2. From here, once you calculate the IB, RI, common mode, turns to be equal to that. R pi over 2, 1 plus beta RE. Again, R pi is not significant, but look at that quantity. It's huge. It is beta multiplied by RE. So if RE was like 100K, like that one, this would be beta times 100K, like 10 mega, the least 10 mega, very high input impedance. Or if it was the modified one, well, it would be 10 mega multiplied by another multiplier here, like 100 or 50 or like 500 mega ohm common mode input impedance. So that is why the differential amplifiers are pictured with this circuit here, with only differential input resistance, RD, V1 and V2, plus and the minus. This is known as the differential input impedance. Differential input impedance. But actually, each one, if you join them, they have an additional resistance from here to ground. RCOM and another one from here to ground. RCOM. It is much more complicated actually. See, the model is this one, but two resistances from here to ground, here to ground. And that is when you apply a common mode input. Actually, this is twice of RCOM, times 2. Because when you join them, when you short circuit them together, you look at the input, you see 2 RCOM parallel to 2 RCOM, it's equal to RCOM, what we calculated over here. R common mode. Here. Input common mode resistance. And it's a very large resistance. Usually we ignore that resistance in the calculation. All right, so What is finally the differential gain? AD is the differential gain, is the differential gain, AD, is actually V1 minus V2 multiplied VO is V1 minus V2 times AD. And this voltage gain, AD, is equal to RC is equal to minus GM of transistor 1 or 2 multiplied by RC divided by 2. So bear in mind that is your differential gain. It's the GM of this transistor which I showed you before in the idealized situation, idealized case. In other words, with this open circuit, infinity. Easily, I showed you that the output voltage is V1 minus V2 multiplied by that quantity, where GM is transconductance of these two transistors, the amplifier transistors. Now, ratio of this guy, 2. Whatever ACOM is for the common has to be as large as possible. And that will define the CMRR, the common mode rejection ratio, which I explained why it is significant. Because when you're connecting the two inputs to a target source for amplification, and that is this example here. When you had, I drew a heart for you, and then amplifier plus and the minus. This is V1, V2, and that's the differential plus minus VD, which is nothing but V1 minus V2, difference of the two. You want the output voltage, VO, to be AD times V1 minus V2, but unfortunately, this point has a common voltage with respect to the ground, known as VCOM, which is usually nuisance, it's an interference. So that voltage is superimposed on that voltage. ACOM multiplied by VCOM. So the actual output of an amplifier in a process, differential amplifier, is the good signal, that tiny little signal, VD, which is the info. This is the info, you can call it. Info signal, the good signal. We want it to be much, much more amplified as opposed to the common mode voltage is amplified. So we want this to be as small as possible, or at least in comparison as small as possible compared to 80. So in a good amplifier, this is a good amplifier. Good differential amplifier. So they created that coefficient called CMRR, which is nothing but the ratio of AD to ACOM. This is the closest they could do. So they said, look, build something, but if you want to sell it to the customer as a good amplifier, what is your figure of merit there? You know, like the coefficient. It's this ratio. The higher, the better. It means in comparison, ACOM is small compared to the AD. So usually it's put into logarithmic. So we get CMRR RdB, which is 20 log of AD over ACOM. So in the specification, you will see how much is CMRR in terms of decibel. Typically 80 dB, 90 dB, 60 dB, while the voltage gain itself is like maybe 100 dB. So let's see what is here. So remember how to calculate our RPi is 7.1, GM is 21 millisiemens, IC is half of the IE current in here. So if this is 1 milliamp and that is about 0.1 of a milliamp, 1.1 milliamp, each transistor is holding half of the 1.1, 0.55 milliamp over there, 0.55. So with that 0.55, you can calculate the GM of each transistor, GM1 equal to GM2. And if this was made with a transistor like this one, Q3, for example, the GM of that, which is involved in here, should be calculated with this 1 milliamp, 1.1 milli. So let's see. High common mode input impedance. We usually don't use that one. It's gigantic. And differential gain. Differential gain is GM times RC divided by 2. You calculated GM over here, multiply by the RC, whatever the value is. It tells you what the values are. RC is 1.28K. Stick it in that formula. So our differential voltage gain is 13.5. It's not much, just 13.5. But let us look at the common mode voltage gain, ACOM. ACOM of that one, utilize this formula here. That one, approximation formula, which is approximation to that exact equation. We calculate that, and it turns to be 5 milli. The gain ACOM is 5 milli, as opposed to 13.5. Then what is the CMRR? It's got to be the ratio of the 13.5 to that 5 milli. So it should be in the next page. I'm going for it, but I hope I won't lose it. Should be here. Yeah, there it is. Yeah, we calculated those. I'm sure it was here. Didn't jump. Okay, so we finished with that page. I have no trust at all in this computer. So here, finally we calculate, yes, that shows the calculation. Differential gain Y is 13.5, it's just there. CMRR is the ratio of these two, 2,385. 20 log, about 67 decibel. So you notice that this gain, 2,385, the ratio means, because this is 2,385 times compared to this one, compared to the ACOM, therefore your amplifier will amplify the difference of the two signals much higher, as opposed to this will amplify the menacing signal ACOM by a gain of 1 times. 1, 2, 3,000. So even if this was like a 1 millivolt signal, V1, V2, which is typically on the heart, 1 or 2 millivolt, you'll get gain of 2,000. So you will get 5 volt peak to peak heartbeats. Here, VCOM is only 1 time. So if you had like 1 volt signal in here, 1 volt interfering signal compared to that, it would amplify 1 time. You will get 1 volt. 1 volt against the 5. So this dominates over that one. So your signal will be much, much clearer. Because we don't know this guy. This is a uninvited stray voltage. and shows up in the output of the process. So the CMRR is responsible for that, the common mode voltage gain. How accurate it can be, your VCOM, how low it can be, the better is your amplifier. All right, so I recommend that you read this part in detail just to understand how it is obtained. All right, so you don't have to worry about this part. This part talks about the feedback. It won't be in the exam because we are not supposed to get there. You will see the feedback when the professor talks about the operation amplifier. I think you have another course, it's called operation amplifiers. Oh, so easy to teach course. It's wonderful because all the professor will do, will show you, this is what we have here. And then imagine things that you can do with it. So they will say, look, this is what we have, plus minus RD differential. We have got a huge voltage gain in here, plus minus AD multiplied by V1 minus V2. And we've got an internal resistance, RO, output resistance. And here is your V1. Here is your V2. Okay? And this is your output. Then from here on, they will start talking about the feedback. What will happen? Every time that they talk about one formation, they will assume that the amplifier is ideal. Ideal means that will convert into an infinite input impedance, V2, V1, going in, having a voltage gain over there, plus minus, no output resistance, zero output resistance going there. And the output voltage will be equal to AD times V1 minus V2. This will be the kind of the simplified ideal model. And then they will say, look, what happens if I take this amplifier, the one we just modeled over there, and I make this VI, which was the V1, and this is the V2. And I make V2 equal to R2, R1, and this is the VO. And this is the internal dependent voltage source, plus minus AD times V1 minus V2. So now that they are interconnected, part of the output is building the input. What is the ratio of output voltage over input voltage? VO over VI. It's just simple algebra. Because input impedance is assumed to be infinity here, there is no current there, known as I feedback equal to 0. So whatever voltage is here, the voltage there is a voltage divider, known as VF, feedback voltage. It's equal to R2, R1 plus R2 multiplied by VO. They define this ratio as B, feedback factor. Therefore, VF, feedback voltage, which is a substitute for V2, is B times VO. Then they will say, this output voltage, VO, is AD multiplied by V1 minus V2. This voltage minus that voltage. This voltage is a fresh input, independent input. But this voltage, the second one, V2, is derived from output by a ratio. Minus B times VO. Then they'll tell you, go use algebra to calculate what is VO over VI. And this will be the universal formula for feedback systems. AD, known as forward voltage gain, over 1 plus B multiplied by AD. That's it, known as feedback gain, known as the feedback gain. Superiority of this formula, or advantage of that formula, is in this product. This is called loop gain. Loop gain is defined as output from broken feedback. So if you break this feedback, nothing. You inject a signal in here, what is going to come out back towards yourself? So pretending that what is coming out of here, if I put 0 here, and I inject the signal there, receive it here, of course. It will be A times, and then multiplied by the division in here, which is kind of a reduction, attenuation. So it will be A times B, known as the loop gain. If you build an amplifier, one of these differential amplifiers, so that AD, BAD, happens to be much, much greater than 1, like 100 or even more. Then look at the formula, what will happen? If this term dominates over 1, okay, that is you ignore 1 compared to that, do you see AD cancels from top and bottom immediately? If they cancel, then your voltage gain will be VO over VI will be 1 over B, which is nothing but 1 plus R1 over R2. Because B was equal to R2 over R1 plus R2. There it is. You get a formula which should be familiar with you if you used it in the past as non-inverting amplifier voltage gain. But at that time, you wouldn't know about differential properties. That brings this up. But in this example, that will be the voltage gain. So what's the advantage of having that? Obviously. The advantage is, all you need here is AD times B to be much, much greater than 1. More than 100 times, that's good enough. If it is 1,000 times, 10,000 times, 100,000 times, even better, right? Because it's really, really then dominating over 1. Formula is real accurate. So, when you're designing an amplifier, you're building an amplifier, you have all those internal stages. You are facing beta here, beta there, beta of this transistor, GM of the other transistor. Temperature, that changes VT, thermal. VT changes, GM changes, gains change, okay? So we've got lots of things that is happening inside an operation amplifier regarding, parameters, internal parameters, RPIs, name it, GMs and so on. Those variations are going to build up, show in the AD, this AD. So this is kind of a not very predictable parameter. The models that I gave you came up to a gain of 200 or 2,000 or 20,000 or 200,000. Those are not completely accurate. It could be 30% off, even maybe 50% off. That doesn't matter. Whether this is 50,000 or it is 100,000, that's 100% change. As long as when you're feeding back, that ratio is greater, it is ADs cancel, you get 1 over B. What you plant here is going to determine the gain. For example, 9K, 1K. 9K, 1K, it makes this 9 plus 1, you got 10. You got a gain of 10, exactly gain of 10. Provided it's more than, this is much greater than 1. Again, how much is much? Minimum 10 times, that's minimum. But if it is 100 times, you're making only 1% error. If it is 1,000 times greater, you're making 0.1% error. 0.1% error in this formula, in that formula. So that is why we have. But other than that, there are advantages. Advantages are, which your professor will line by line do it for you. Then you know what they will assume? They will assume now, they've got this picture for you. What happens if we had a resistance in here, RD? If you did that, you can very easily show what will be the II. This voltage is equal to V times VO, that voltage in here. And if you calculate V1 minus V2 and you divide it by II, it is possible to show that the input impedance R in with feedback will be equal to RD multiplied by 1 plus B times A. Then you will say, now check this out. You're making an amplifier, RD is 10K, like this one we had. It was 7K. Do I have to worry about it, like having a low input impedance amplifier? Answer is no, no worries. Because when you feedback, the input voltage divided by input current will be this much, which is RD of what you built, maybe as low as 10K or typically 200K, multiplied by the B, typically 1/10, the least is 1/10. A's go to thousands or hundreds of thousands. So we will have hundreds of thousands of 10K. That goes to gigaohms. So it will give you very high input impedance amplifier. Also something else will come up here. Output impedance. They will say, now what if I had a resistance here, internal, RO. You know that 1 or 2K collector resistance making the final one. No worries, because here are out from this port, RO with feedback, RO with feedback would be the one without feedback, RO, resistance of that final stage, divide by 1 plus B times A. Again, this quantity runs to tens of thousands. So even if you had a output impedance from the last stage, like 100 ohm, or maybe a kilo, that kilo will divide by 100,000, and that will be milliohm output impedance. So this amplifier will have milliohm after feedback. And that is why when you connect amplifiers of that kind to speakers of only 8 ohm or even less, it wouldn't matter, because the feedback will make the output impedance from your amplifier look like milliohms. Very, very small, this one. So if that is like 50 ohm, and that is 100,000, the output is only fraction of a milliohm. So when you put the speaker in, this the output level is not going to drop. So the amplifier compensates for that. You know, your feedback compensates for that. Have you noticed we've got this much output impedances, and then how come it can feed an 8-ohm speaker? 8-ohm speaker has such a low resistance that why when you connect it doesn't drop? Well, because it has a feedback mechanism which automatically reduces the output impedance, makes it ideal, makes this thing ideal Thevenin. When you look back, this is the Thevenin, which is almost like ideal because it's so small. But if without it, if you look back, you will have that RO. So if this was 50 ohm and this 8 ohm, well, you would lose a lot in the system, in your output power. So that is the completion. This thing is the completion of this amplifier business. And then something else that we did not discuss, but you will be needing, but I gave you a handout on power. Let me tell you which one it is. So if I go to, so this was homework number, so that one was on homework 5, I think, yeah, here. Right there. I'll go to the next page. All right. Consider that stage, that one. This is always a final stage for every power amplifier. Every power amplifier. So the basic amplifier, differential amplifier goes like this. Current source, IO source, and then the differential, and then it goes to with a resistor, which is not really necessary, but we can do that. So here is an additional amplifier. So from here to there, I'll take it from here. From here to there, we have inverting from this input. We get inverting, and then it goes to another PNP transistor. Sometimes they put resistance there, optional, and then here to negative VCC, this is the RC, and this will be the, and also from here to here we have another inversion with respect to that input. So from here to there, it is non-inverting, because base to collector is one inversion, base to another collector is another inversion. So those two are in phase. That's why this will be marked plus, and that will be marked negative. It's the opposite. From here to here, it's no inversion. From here to here is inversion. That's why this will be designated as the negative input. So this is our amplifier, V1 and the V2. The amplifier that we have built. This provides gain. RC is the output resistance if you try to connect that directly to a load. We can't do that because these RCs are very high in order to obtain a high voltage gain from that stage. So what they do, they take that to this particular amplifier. In an unmodified form is what I'm trying. This is not modified yet. Then this will go to a low resistance, RS. So this is known as the buffer. It's like an emitter follower. Emitter will follow the signal over here. For positive going signal, the upper transistor base will go positive. Therefore, the current will go into into a positive conduction. So this is positive, this will go positive, and the current will go in the direction of the arrow, towards the load, into the load. For negative inputs, here, negative phase from the zero, practice to make that equal to zero. For negative input, the voltage in here will go negatively. The emitter there will follow that negatively. So this is the emitter of the PNP, but that one is the emitter of NPN. So this is PNP, that's the NPN. That will constitute your final output voltage. This is a power stage. It's capable of driving a lot of current into the load because it's going out of the emitter. Unlike this guy, this is unable to provide that current to the load. Why? Because the current in this stage is typically a biasing current. You know, like milliamps, 5, 10 milliamp, that's it. But in here, you have a booster that when the current goes out, it will be amplified by the beta of each individual transistor. Why do we need two? Because without one, yes, when voltage was positive, emitter will follow with an offset of 0.7 down from here, it will go positive. But when we get to zero and the current has to reverse, if this goes negative, the current has to come in. The top one won't be able to do that because this is only sourcing current. This guy, sources current, load current, I should say, load current. This one sinks load current. It means drives in the opposite direction. Okay. So that is how the issue of a sinusoidal wave is taken care of. Otherwise, if you had only one, for the sinusoidal input, you would get a half-wave rectified waveform at the RF. Well, that's not acceptable because music is full fluctuation of the voltage, both positive and negative. So it is a must that we've got to have these two types. You always have these two, it's called complementary pair, because they come out of factory matched. They match their betas, match the IS, every part of the characteristic together. They sell it as a pair. A single one has no value because it has to be paired with the two. Because base current for the positive one relies on the beta of that one. Load current divided by beta of the n-type is the base current. When that goes negative, you get negative current. It has to be the same beta to give the same current, or else it will be nonlinear. It will be messed up. Now here is the problem. This is called a class B. Class B amplifier. Only class B amplifier. Class B amplifiers are very efficient, but they have one problem, and that is this thing. Their voltage transfer characteristics looks like that. There is a dead zone at 0.7, positive, 0.7, negative. Meaning that the orange one has to go above a 0.7 of a volt in order for the top transistor to pick up. Because VBE, if that voltage is less than 0.7 and this is a 0, you're not going to have any current in the emitter. So this will be like flat 0. Output voltage will be flat. That's why you will have this flat output, 0 from here to here, while the input voltage hasn't exceeded 0.7 of a volt. Similarly, For the negative one in here, you need again positive 0.7 from here to here to have an emitter current. So that means until the input voltage goes to negative 0.7 in here, there is no output there. Here. Two flat zeros momentarily when a sinusoidal drives the input stage. So if the sinusoidal voltage is way bigger than 0.7, this distortion will be almost unnoticeable. I mean, not significant. But if the signal is small, which in the case of we are playing low music, it is small, you need to have, you need this thing to disappear. So how do they do that? They do it with a compensation. So we need to put a kind of a DC voltage from here to here by 0.7, another DC voltage from here to here by another 0.7, in order to make up for VBE 0.7 of each transistor. And there's a way to do that. Now, here is the main advantage of the beta. There is something called power efficiency. Read this calculation first. Power efficiency is amount of the power that power supply delivers to both transistors and the amount of power that gets out to the load. I did a calculation in here. The power efficiency of this configuration will reach a maximum. The formula for that is eta, which is P to load divided by PS delivered by both supplies, combination of them, times 100%. Okay. So I showed you over there that the power efficiency of this class B, for this particular one, is equal to that, but we can formalize it. The formula, official formula for the class B, known as efficiency equation for class B, is equal to eta pi over 4 multiplied by V I M, this is the peak input voltage, which is this guy here, V I M, or maximum voltage, which is symmetrical, the same thing as the negative. In other words, the peak input voltage, amplitude, divided by VCC, multiplied by 100%. So this is the official textbook formula. You will just Google efficiency for B class, this will pop out immediately. However, mathematically it has a value because, check for yourself, how far this amplitude can go. Because it seems the higher it is, better efficient it is, right? The higher is the VIM compared to VCC, the better it is. But how high it can go? Can it go twice of supply voltage? This voltage, can it go twice of the VCC? No, because you have 48 volt at the collector. Do you remember what we said? For guy to stay active, base voltage, collector voltage has to be 0, no more than 0 compared to the base. This has to be higher than 0 with respect to the base. So the maximum base can go is to 48 volt. Then this will be 48, that will be 48, emitter will be 48 less by 0.7, just a tad short of. You can calculate the peak voltage across the resistor, and therefore how much RMS you can produce across that resistor. Therefore, the final output of your power amplifier, this power amplifier, very easy. So 48 is the maximum here, approximately maximum over there. Then you can calculate how much power will be there. 48 over radical 2, that will give you the RMS. RMS divided by 8 ohm, if it is 8 ohm, it will tell you how many tens or hundreds of watt it is. So you can design accordingly. Choose your power supplies accordingly to deliver a power that you want in here. For example, this is a 8 ohm. We've got 8 ohm speaker. I need 100 watt speaker. Okay, so this is how I will calculate. Watch. VO RMS squared over 8 ohm must be 100 watts. What is VO RMS? Square root of 800. What is the square root of 800? It should be something like 30. Here, 800 square root, where is it? 28 volt. So this is 28 volt. But what is that? 28 of RMS. It's not yet the peak. So what is the peak in here? Because the transistor should be able to go, right, to the peak. 28, so VO peak, which is approximately the same as the supply, should be radical 2 multiplied by 28. Guess what is that voltage? Here. 28 times 1.4. 40 volt. 40 volt. So you need to set this power supply, gentlemen, here, to about 40 volt, or maybe 40 few volts, 41 or 2 volts, so that the emitter can rise to the vicinity of 40 volt, creating a peak voltage, sinusoidal voltage across the load, that sinusoidal voltage can reach 28 volt of RMS, so that in the 8 ohm resistor, it can produce 100 watt sound energy. See? So that's how you will design your plus VCC, 40. You need symmetrical, negative another 40 for this one. Of course, 40 is not enough, because this base usually doesn't go and reach all the way, it will run out of bias. It should be like 10%, within 90% of the 40. So I would say, if it comes to 40, your calculation, go 45, 46, you see, for the power supply. So there will be a little room for the maximums, because you've got biasing to do in here. It feeds the rest of the amplifiers in here. So this is your final stage, formula for efficiency, and the efficiency here will be interesting to check. If this is equal to 1, that is, supposedly it reaches all the way to 40, then you get pi over 4 times 100, and that will be 78% efficient. This is the best efficiency you can get out of the class B amplifiers, 78%. They're pretty good efficient. You can't get to 100%. There's no way of getting out of that one. However, the menacing part is this distortion that exists between the two. This guy. This crossover distortion. It's called crossover distortion because duty of conduction is passed from one to the other. There are crossovers. So this is how it is modified. They need to take the slack for that 0.7 volt VBE. One of the ways doing it is is this the right page I'm going to? No, I don't think. Let's see. this is page 2, so I'm aiming for page 3. I totally lost the confidence in, yeah, page 3. Okay, so they put actually this assembly here. The cheapest way. A diode here, a diode here, a resistor here, identical resistor here, minus 4D plus 4D, and say 10K, 10K, exactly symmetrical. So when you did this, this voltage in the center is going to stay exactly at the 0 because it's symmetrical supply. When it sits at 0, the diode allows 0.6 volt, this allows 0.6 of the volt, that is 0.7 of the volt. So it grossly compensates for the 1.4 volt with this 1.2 volt. See, this is a 1.2 from here to here. And then the amplifier, instead of using that one, it will feed this section with the PNP to the differential amplifier, etc. So that last stage will feed this point up and down, and those two diodes will compensate with the 0.7 volt drop that is needed between base and emitter in order to avoid that crossover distortion. So this eliminates the crossover distortion greatly. But there is a better one, more professional one, and that is, if instead of these two, you come up with a resistor R1 and R2, and you put a transistor, a third transistor, X and X, the voltage in here, VCE of transistor 4, will be equal to 1 plus R1 over R2 multiplied by VBE of transistor 4. This is the VBE. It's a standard trick that you can build a circuit like that, replace both diodes with this type of a circuit. If you make R1 equal to R2, watch this, R1 equal to R2, look what will happen here. That ratio will be 1. 1 plus 1 is 2. 2 times VBE, so if this is 0.7, it will duplicate to 1.4 between these 2 points. It will be complete match to the 1.4 needed between these 2 transistors. So see, that's the trick. So how do they fine tune that 1.4? We're talking 1.4, but who knows? Might be 1.3 or we might be 1.5. So this is how they do it. They make this one into a potentiometer. They connect that one to the center of the potentiometer. One side of the potentiometer plays the R1, the other part plays R2. And then they start adjusting that potentiometer till you get the desired VCE to exactly match the 2 transistors. And the criterion for matching is build voltage in here till you see a minute current going through the both transistors. Say